The last time we met, we were talking about routers. We were talking about the World Wide Web and how it's composed of many routers all connected in a partial mesh. For example, this router may be connected to multiple routers, yet this router may only be connected to one. One of the questions we asked was, what is the fastest route to get from one router to the other? For example, from D to B. That message could take this route, that's 1. It could take this route, there's 2, or it could take this route. So in this very simple diagram, there are 3 different paths. Which one is the best path? Well, that very much depends on the network traffic. For example, if there's considerable traffic flowing between nodes B and E, the fastest route from D to B is probably going through C. The good news is that all of the routers will keep track of the potential paths using something known as a routing table. Continuing with our previous example, to get a message from D to B, the router, that is router D, has a routing table. It knows that it can send the message to router E, or it could send the message to router C. Both are valid paths to get to B. At a particular instant in time, it will have a metric. That metric for E might be, say, 5, but the metric for C might be 1. Given this choice, the router D will send the message to router C because it has the lowest metric. But that's not the end of the story, because all router D has done is forwarded that packet over to router C. Router C also has a routing table. It could take multiple paths. It could send the message directly to B, like that, or it could send it to E. It's even possible to send it to D. Each of those will have their own metric. In this particular case, router C would then forward the message back to B. In case I didn't mention it, these routing tables are dynamic. They can and will change based on traffic patterns. For example, if this route is very congested, we would expect this number here to change, and we would also expect this number here to change. It's that change which would suggest that it's better to send the packet through the D to E, E to B route. The last time we met, we were talking about a model. I believe it was application, transport, internet, and link layer, where you interface at the application level. One application was HTTPS. Your request flows down through these various layers and then heads out to the World Wide Web. We mentioned that the MAC address lives here at the link level. The IP address lives at the internet level. And there's something called a transmission control protocol, which lives at this level. In fact, it's these two acronyms that give us the name of this model. This is the TCP IP model. As far as this model is concerned, there's some things you need to know. At the application level, we start with data. So you have some data that you want to send somewhere. That data is handed to the transport layer. We'll come back to this in a moment. For now, just know that it adds TCP information to the data. Both of these are then handed to the internet layer. So we have the data, the TCP. To this, the internet layer adds the IP address. These three get passed to the link layer. There's the original data, the TCP, the IP, and now the link layer adds the MAC. Actually, let's redraw that because it adds something else as well. So we have the MAC, the IP, the TCP, the data, and the error correction codes. So that's the frame check sequence. Collectively, we would call this whole thing a frame. Let's take a moment to write down some of these concepts. If we are concerned with the link layer, we're concerned about getting data from one node to the next node. The internet layer is concerned with getting data through the network of routers. And finally, the transport layer is concerned with packaging and then reassembling the data. One way to think about all this is to look at how information flows from your computer to another computer. This is your computer, application, transport, internet or network, and then the link layer. Your local computer talks to a switch. That switch operates at the link layer. It's concerned with the MAC. Your switch is likely connected to a router. Now, a router is going to have two layers. It's going to have a link layer, and it's going to have that network layer. Keep in mind that the link layer is concerned with the MAC address, whereas the network layer is concerned with the IP address. In a very simplistic way, you could say the routing tables live at this level of the router. They live at the network level, where each router selects the best route. So switch is based on a link, whereas a router is based on the network. Your data is sent to another router. Again, there's the link layer and the network layer, where this router determines the best route. Finally, your information likely lands in another switch operating at the link layer before finally going into the server on the far side, where the information is passed through all the layers. So it goes from the link layer to the network layer to the transport layer and back to the application layer. As we said, the link is concerned about getting data from one node to the next node. Your computer has a MAC address, so there's a to and a from associated with that. Your switch on this side has another MAC address, so it's another to and from. Each time we go machine to machine, those MAC addresses are stripped away and then re-added, so we can go from one machine to the next. So to and from. As far as the routers are concerned, you might want to think of it this way. This is your home network. Home sweet home. Where this last octet is the IP address assigned by your DHCP server. This is another network. So maybe that's 75.10.10.5. And finally, this is the network you were trying to reach all along. For example, 2607, F8B0, 4006, 814. or better yet, 0814.200E. By the way, this is something new. We'll talk about this in a moment. This is an IPv6 address, not to be confused with the older and shorter Internet Protocol version 4. At any rate, switches are concerned with those MAC addresses, whereas routers are generally concerned with the IP addresses. For your note card, the MAC, that's something we've seen in lab before. There are 6 octets, and that is in hex, which means there's a total of 48 bits in a MAC address. An IPv4 address, that's similar to the one we used in the lab, so that's 192.168.1.104. There are 4 octets, and that's in binary coded decimal, which yields 32 bits. And the one we just mentioned before, IPv6, there are 8 groups of hex, so that's 4 digits in hex, which gives you a total of 128 bits. You may ask, why did we move to version 6? And the simple answer is, we just ran out of bits. In IPv4, you could have 2 to the 32nd unique number of IP addresses, which in theory led to 4.3 billion. That may seem like a large number, but not really when you think about how many devices you own. For example, a computer, a printer, a game console, maybe one of those new internet TVs, a cell phone. It all adds up, and it adds up really fast. So we move to IPv6, which now has 2 to the 128 possibilities. So I'm not even sure how big that number is, but it's 340 times 10 to the 36 possibilities. So chances are, with IPv6, we're not going to run out of IP addresses. Speaking of IP addresses, let's do a quick sidebar here. Your home system is likely connected to the internet. You likely have a router, perhaps a cable modem is what you call it, but either way, it's essentially a router. That router will be connected to a switch, and then your various devices will be connected up to that. Laptop, cell, game, maybe your music player. Okay, so all of the devices in your house connect up to the switch, which connects to the router. You could think of this as a local area network in that direction, and in this direction you could think of it as a wide area network. We mentioned that the internet is full of routers. However, as far as the internet is concerned, your home system appears as if it has one IP address. So to the rest of the world, you may appear as 72.105.25.10 or something like that. You can look it up if you want. Just search the web, find my IP, and it'll tell you what that is. On this side of the router is your home network, which means you have many IP addresses within your home network, but as far as the internet is concerned, everything about your home network appears on this IP address. That is something known as network address translation, otherwise known as NAT, which is very useful because it allows us to reuse all those IP addresses. For example, there are probably tens of thousands of home networks with the address of 192.168.1.100. However, from the World Wide Web's perspective, they don't exist. Instead, each home address is assigned a simple IP address such as this. It's up to this network address translation to take a piece of information that's meant for your laptop and make sure it gets to and from the internet. Likewise, it takes something for your music player. Make sure it gets to and from the internet. Moving back to our main conversation. Where were we? We were talking about the TCP IP model and how we add data at each layer. And I did say we would come back to this transport control protocol. So let's go ahead and do that now. Suppose you just took a picture of your favorite animal, which is something that occurs at the application level. Now, this is a really big picture that you just took. In order to send this picture over the internet, it has to be broken into many packets. This is something that happens at the transport level. Let's go ahead and break this into n number of packets, where each packet contains a binary number sequence. Each piece of information, but only one at a time, is sent to the internet level. For instance, let's take the first piece of information. It's sent down here to the internet level. It is placed into an envelope with from and a to address. Turns out these are IP addresses. From the internet layer, it's sent to the link layer. I suppose you could say that this envelope is stuffed into another envelope that has a from address and a to address. The difference is that this time, these to and from are based on the MAC. From there, this envelope is sent to the hardware. It's sent to the network interface card. And from there, it's sent on your wires. So you have unshielded twisted pair, shielded twisted pair, maybe coax. No, probably not coax anymore, but it could be over fiber or maybe wireless. So let's look at that again. At the application level, we have this picture of a squirrel. That picture gets broken in to many different packets. Each packet, one at a time, is sent to the internet layer, where it's given an IP address. From there, it's sent to the link layer, where it's given a MAC address, and then it goes across hardware. On the other side, this works in reverse. A frame is received, which is nothing more than a bunch of ones or zeros. The link layer recognizes the MAC. If the MAC is indeed for this particular machine, the data is then passed up to the internet layer. The internet layer strips off the IP address and passes it to the transport layer. The transport layer makes sure that the information is received. Well, first off, it makes sure that it's received in order, but it also checks to see if there's anything missing. If there's things missing, it will request the information be resent. So in the end, the transport layer presents the complete picture or file or whatever you're looking for to the application layer. All of this is a fancy way of saying that information is added at each layer. The transport layer adds TCP information, which allows it to reassemble things in the correct order. The internet layer adds the IP address, which allows it to get through the field of routers. And the link layer adds the MAC address, which allows it to go from one machine to the next. With that said, let's slide over to a new but very much related concept. We've already talked about routers to a certain extent, and the fact that the World Wide Web is full of routers. There has to be a way to get from, say, YouTube, which you're watching this video on, and your home. In order to make the system work, each router has to be able to very quickly look at an IP address. It has to be able to ask, is this my information or is it not my information? One aspect of this is the ability of a machine to look at an IP address and split it between the network identifier and the host identifier. So network ID and the host ID. This is done with the help of the subnet mask. In fact, you saw this in lab. 255.255.255.0. We've been playing with this for a while. If you take the number 255 and you convert that into binary, you end up with 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 ones, another 8 ones, and yet another 8 ones, and then 8 zeros. Here's how that subnet mask works. Suppose you have an IP address, 192.168.001.105, and you have a subnet mask, 255.255.255.0. We've already established that 255 means 8 ones, so there are 24 ones and then 8 zeros. This piece of the IP address would be the network ID, and this number would be the host ID. To be fussy, this network is described as the 192.168.1.0 network. The host is described as 105. In some places, you may see the network identified as 192.168.1.0/24. This 24 tells you how many ones are in the subnet mask. So if there's 24 ones, we start on the left, 1, 2, 3, 4, 5, 6, 7, 8, 16. There's 24, and then there would be 8 zeros. Once again, where this is the subnet mask, the 24 leading zeros are used to identify which part of the IP address is used for the network identifier. And the part that's not masked is the host ID. That brings up the question, how many hosts can be on a network? For this particular case, if there are 24 bits for the network identifier, that leaves 8 bits for the hosts. How many things can you describe with 8 bits? Way back from day 1, you'll remember that that question is answered as 2 to the n is equal to the message space. In this case, 2 to the 8, which is 256 potential hosts. However, we do reserve .0 and .255, which means that there is a maximum number of hosts in a /24 network of 254. But not all networks are /24. For example, suppose you were given this IP address. We want to know the network ID, the host ID, the subnet mask, the number of hosts. On a /16 network, the subnet mask is 1, 2, 3, 4, 5, 6, 7, 8, so 8 ones, followed by 8 more ones, followed by zeros, followed by 8 more zeros, which means the first 2 octets determine the network ID. So in this particular case, we just split it like so, which means the network ID is the first 2 octets. We may as well add the /16 here, whereas the host ID in this particular case is host 2.4 on the 73.218 network. The number of unique hosts is 2 to the 16th minus the reserved numbers, which gives us approximately 65534, assuming the lowest number and the highest number are reserved. We should at least acknowledge that there are other ways to split the network. In this video, we looked at a /24 network, which yielded about 254 unique hosts. The /16 network, which allowed 65535. Without too much effort, you could visualize the /8 network, which would allow 2 to the 24 minus reserved, which allows 16,777,214 unique hosts. In each case, you can see that we split the subnet mask on the octet. That /24 network had a subnet mask of 255.255.255.0. The /16 network, and finally the /8 network was 255.0.0.0. In each case, we split evenly on the octet. Here's 3 octets of 1s, 2 octets of 1s, and a single octet of 1s. Know that this is a clean and easy way to do it, but it's not the only way. For example, we could just as easily have done a /22 network. This is not a difficult concept. However, it's beyond the scope of our electronic communications class. If you're interested, go take an introduction to computer networks or research it yourself on the web.